Welcome, everyone, and it's a pleasure to welcome you to tonight's webinar. My name is Paul LaChapelle. I'm with Montana State University and happy to be hosting the webinar this evening that was supposed to take place at the Museum of the Rockies, but we're very happy to be hosting it online with you all. Just want you to bring your attention to any tech support needs that you might have. You can see some tech support information in the chat box that's at the lower right-hand corner of your screen. If you just click on that to expand the chat box, you can see some information there with a web address or a email address and a phone number. Feel free to call or email if you have any tech support questions. There's also different ways that you can view this WebEx platform, and depending if you're looking at this through the app or the browser, there are different types of three different viewing settings that you can choose yourself. So feel free to play around with this or type questions into the chat box for our presenter or in terms of tech support questions that you have. We are recording the webinar and it will be posted on the Gallatin Valley Earth Day website, and you'll hear a little bit more information about that right now. It's my pleasure to introduce Ann Reddy. Ann is the chairperson of the Gallatin Valley Earth Day, and she is going to say a little bit more about the Earth Day events and about our presentation tonight. So I am going to give Ann the microphone rights. And go ahead and take it away.
Thank you, Paul. I wanted to welcome you all tonight and thank you for joining us tonight for this very interesting talk. I heard Randy talk a few months back at Montana State and found it so interesting that I asked him to come and give another presentation as part of Earth Day. So thank you, Randy. As I said, this webinar is part of the Gallatin Valley Earth Day celebration. And it would not be possible without the generous support of our partners and sponsors like Montana State University Extension Community Development. I'd also like to thank Obo's Footwear, Sacagawea Audubon Society, Bozeman Green Build, who you'll hear from the owner, John Palm, in a few minutes, the Bozeman Daily Chronicle, and the Greater Gallatin United Way. I would also encourage you to join us for additional webinars celebrating the 50th anniversary of Earth Day, especially during the week of Earth Day, which is April 18th through the 25th. For more information, just check our Facebook page, which is Gallatin Valley Earth Day, and our website, which is at www.gallatinvalleyearthday.org. Now I'd like to introduce John Palm from Bozeman Green Build, and he'll just say a few words. Take it away, John.
Hello, everyone. Thanks so much for attending tonight's seminar, especially in light of all the craziness going on. Give everybody a break from Netflix, which I'm sure is welcome. I am just going to speak briefly about some of the projects that we've been doing right here in Bozeman that are near and dear to us because they are benefiting the Bozeman School District directly. After about 29 years of working in sustainable building and renewable energy and doing solar systems all across the state at breweries, food banks, ranches, farms, libraries, fire stations, and of course, residences. This last few years, we've seen a really exciting uptick in the number of systems being installed at schools. One really neat thing about this is that these systems are at the 50 kilowatt size, which some of the participants tonight might know is the limit that we can do in Montana on Northwestern Energy's lines and still be net metered. So we are seeing systems built as big as they can be, and they're being built all over the state In 2017, a student at Sacagawea Middle School stepped up and launched a fundraising campaign that got the Bozeman School District projects off the ground and up and running. We ended up building that first 50 kilowatt system at Sacagawea, and we made the decision to do it at cost so that enough money could be carried over from that project to then provide the seed money for the next project. Bozeman School District then turned around and did 2 more systems at Highlight and Meadowlark schools, and then a third system last year at the Support Services building. So to date, the district has built 200 kilowatts of solar just in the last not even 2 years. And other districts around the state are following suit. Billings now has 3 50 kilowatt systems at 3 of its high schools. The Helena School District just built 3 new elementary schools, and in the planning phase of that project, they committed to putting 50 kilowatt systems on all 3 of those schools. Small school districts around the state have also jumped in and are building 50 kilowatt systems, for example, in Lavina, Big Timber, White Sulphur Springs. So we're seeing a really great trend toward public infrastructure adopting solar PV, partly because there's a funding stream, a partial funding stream that comes from a state tax, and also because they realize that it's a great investment. For example, the 4 systems plus the 2 that Bozeman is going to build next at Morningstar and Emily Dickinson, when those 6 systems are all up and running, that'll equal about the same amount of money as it costs to hire 1 starting teacher in the school district. So 6 50 kilowatt systems, each making about $5,000 a year in energy savings, will equate 1 new teacher. So I'm very encouraged by the trend that we're seeing. There's also a lot of adoption of solar PV in the nonprofit sector and in other government buildings. I think all we need now is a bigger injection of infrastructure funding, which could, because of the current crisis that we're seeing with COVID-19, potentially come in some sort of Recovery Act monies at the federal level. So I'm hoping that all of this leads to some sort of solar schools bill or public solar bill that will eventually make its way to Montana and allow us to adopt solar at an even greater rate across the state and build out this infrastructure, which is so important for myriad reasons, which Randy is going to be addressing next. So with that, I would like to thank everybody again for coming and encourage everybody to, whenever they have the chance, to let folks know who are our representatives at the state level, and John Tester and Steve Daines and perhaps Steve Bullock. Let them know how important it is that if we're going to be spending public dollars on stuff, it might be a really great idea to spend it on public infrastructure, including schools, in the form of renewable energy and solar PV. So Randy is next, and it's a great segue for me because we've worked together a little bit. We've done a little bit of solar on some of Randy's projects, and I know that Randy, for years and years now, has done his best to incorporate renewable energy into most of his projects. So with that, I would like to make a formal introduction. Randy is based in Billings at High Plains Architects. High Plains is dedicated to sustainable architecture in the region. They just completed a building called the S by S building at 387 Gallatin Park Drive, near Mount Brewing, down in that area. It's the first privately owned LEED Platinum building in Bozeman. Randy is a licensed architect and LEED accredited professional with the building design and construction specialty. He was made a fellow of the American Institute of Architects in 2014, and he holds a bachelor's degree in architecture from Stanford University and a Master of Architecture degree from Yale University. Take it away, Randy.
Okay, thank you, John, and thank you, Ann, for the opportunity to speak tonight. Of course, I'm very excited to be speaking at an Earth Day event. As the title here might suggest, we're trying to save the planet. We've been trying to do that for 50 years. We should have started a long time ago. But in any case, we're doing it now. So I would like to start just very briefly with a little commentary about what's going on right now. Obviously, we're doing this by remote control, if you will, because we're not able to all be in a room together. So the COVID-19 virus that's spreading around the planet is certainly an incredibly serious issue, and I do hope that all of you are safe and well in your respective locations. But I just want to be sure that we don't forget and take our eye off the really critical issue of climate change, which could lead to our ultimate demise. So I'm going to say that climate change trumps COVID-19, not that COVID-19 isn't incredibly important right now as well. So with that, we'll move along to, whoops, I'm supposed to have figured out how to do this. Oh, there we go, this button. Okay, I'm going to talk a little bit about my journey just as, for a little bit of background. It started in 1972, as John mentioned. I went to Stanford as an undergraduate. So in 1972, when I was 18 years old, I left the long view and big skies of Montana on the left, and I arrived in something that looked not quite as bad as that picture on the right, but pretty close. So I went from, although you're seeing a road on the left, I didn't necessarily think about myself as being car dependent. I got to California and you couldn't go anywhere without a car. And so that was kind of a big shock. I didn't have a car at the time. I rode my bike everywhere. But nevertheless, shortly after that, in 1973, we had the first energy crisis. And not only was gas suddenly not 25 cents a gallon, it wasn't available. And in California, you had lines for miles, people trying to get a few gallons of gas to keep going because they really couldn't function without it. And for me, that was a real eye-opening moment, and it really brought home this idea of limits, something which up to that point in my life I'd never really thought about, and now all of a sudden I'm kind of right in the middle of it. So from that, and the fact that I was just a young student, it had a major impact on my interests in architecture going forward. So everybody's got to have some elephants in the room. So we're going to start with the four elephants in the room. Starting with energy consumption, fossil fuel consumption. I want you to notice the timelines on all of these too. This particular one starts in 1860 to 2000, so it's 140 years. The lines, of course, have continued to escalate and climb. We could move the coal portion of this back to about 1750, but it's a relatively short time frame that really didn't take off until right after World War II. But all of a sudden, we start to see a steep increase in the usage of fossil fuels. World population, this is over the last 12,000 years. And as you can see, up until about 1700, the line was relatively flat. It just started to turn up about 1700. So 1750 and up, I mean, that's when this began to really take off, when oil and other fossil fuels really began to be used in significant extent. Population went nuts. This is a 800,000-year time frame, looking at CO2 concentration in the atmosphere. It certainly fluctuated up and down over that time. There were several ice ages during that period. But then again, right around 1800, we were at a relatively high point compared to previous peaks, but we have continued to accelerate at a very steep rate, really unprecedented in modern times, or really in human history. And lastly, we have the human population increase as compared to species extinction over the last couple hundred years, all again coinciding with this increase in the use of fossil fuels and population increase and so forth. All of these curves look a lot alike. They're relatively flat for a long period of time, and then all of a sudden they take off. And they've taken off, especially in our lifetime. So what does all that mean? Well, if you take the fossil fuel dependence and add the population growth and add global temperatures and species extinction all together, what you get is trashing the planet. I took the animation out of that, but the planet got dropped in the trash can. So the important thing to note here is that assuming present trends continue, the odds are quite good that we'll become the best informed extinct species on the planet. And it's very important that we remember that the planet really doesn't care if we're on it. We have to care if we're on it. And if we don't, we might not be on it. So we have a problem and we need a solution. The problem is that we're trashing the planet, and the solution is that we need to learn how to live with the planet instead of on the planet. And that's what we've really been focused on in our practice for the last 20 years, and for me, since college days. So I put this up here because if you look at North America, right where Montana is the last best place. It's important because we have a really incredible opportunity to do things in this place that we can't do everywhere else. Montana, fortunately, isn't done yet in the same way that the rest of the continent is. And we still have a tremendous opportunity. So I've looked at that for myself as really the opportunity to expand beyond the current thinking and try different things. So when we first opened the office in 1999, was our opportunity. One of the reasons we opened High Plains Architects is because I wanted to be in a position where I could really get into these issues that were of critical importance to me and explore ideas that I wasn't able to do in the same way that can happen when I'm working for somebody else. So we began simply with some smaller houses, looking at passive solar design, well-insulated buildings using SIPs, structural insulated panels, or straw bale construction. We learned a lot about stack ventilation and how effective that can be. Moved on to some commercial buildings. This particular building actually was our second office. We bought it in 1999, but didn't move in until 2001. It was the first mixed-use downtown housing, so that was new. But we also incorporated radiant floor heating, evaporative cooling, and some other strategies to really begin to look at how we could take an old vacant building and make it into not only a useful contributing member of society, but also make it into a higher performing building. And as part of that process, we really learned that tearing buildings down is an incredible waste. So again, we've got the 5 votes in favor of saving and 1 vote for stomping it to bits and eating everyone inside. We're always on the side of the 5 votes in favor. It really is, in our experience, cheaper to save and remodel than it is to demolish. And that's actually always the case, as long as you listen to the building. So one of the first principles that we've learned when it comes to dealing with sustainability and figuring out how to live more lightly on the land is to take advantage of resources that already exist. So reusing, repurposing, and restoring existing buildings has proven to be a great resource for us. And we start as this photo shows with listening to the building. That's, for an architect, a really big deal, because it's not about coming in and stamping some new ego on top of it. It's about understanding what that building is, what it has to offer, and learning how to work with those things. And by doing that, we can do we can take buildings like these and make them into something. The one on the two on the left are the before pictures. The two on the right are the after pictures. In both cases, those buildings have been vacant for decades. The one on top, of course, was a very prominent building in Billings, and it had become largely vacant. Well, really vacant, totally vacant, but largely vacant for over 10 years at the point that we took it over. Employed those same kinds of approaches, stripped off the decades of sins, added some high performance features, and made it work a lot better. Principle number 2 that we've learned is don't wait for the change, be the change. And so what that's meant is, as we've looked at things like these old buildings, we find that a lot of times people are reluctant to pursue those because it seems way more complicated. And what we've learned is that no, there's a lot of advantages to taking that kind of a resource and starting with that and moving it forward. And we can make better buildings for less money. So we have undertaken a lot of that being the change to heart. So these are just a few snapshots of various buildings that we've redeveloped downtown. All of these buildings were vacant for anywhere up to 25 years. And we've taken them and put them back into play, all the while looking also to make them as high performance as we could, as we've learned along the way and how to do that, because the idea was that they've been around for over 100 years. We need to set them up to be around for the next 100 years, to be durable, to be efficient, and to be able to last and be buildings that people will care about. So that leads to principle 3. As we've gotten more and more involved in these downtown buildings, we've wanted to focus on recreating downtowns and making communities walkable, and thereby being able to reduce the need for automobile transportation, making things on a more macro scale than just at the building level, more efficient, energy efficient, resource efficient. So all of these things are starting to come together to help each other out. Again, these are some of the buildings that we've done. These are the walk scores that each of these buildings has, so that they're all located close to lots of other amenities, lots of other attractions, lots of other services. These buildings, most of them contain housing, and many of them are mixed use, so there's housing up above and commercial uses on the lower levels. So principle number 4, high performance. That as we got further and further into these buildings, we discovered that they had a lot to offer in terms of being able to become a high performing building. And part of it we realized is that it's because when they were built, they didn't have the opportunity to just insert systems and import utilities, gas, electricity, to make them function. They had to work better with just taking advantage of the architecture to bring in natural light, to be compact, to be close to other buildings, so that they could work well without a lot of outside inputs, which didn't really exist yet. Now, all that started to change, of course, after World War II, as we saw. But achieving high performance in these older buildings was an exciting thing that we discovered and that we have continued to pursue. So again, some of these things are things that we've just learned along the way that have turned out to be very helpful to us. But the first thing here, this 4-step energy strategy, has to do with figuring out how, again, to reduce demand for energy and outside inputs to the greatest extent. So the first thing we can do is optimize the building envelope. And we've gotten to the point now where we don't pay any attention to what the energy code says about insulation levels. We want to optimize insulation levels for the particular building, for its use, and for its location. Another thing is recycling waste heat flows. And now it's not even just waste heat, it's waste water, because our whole system is built on one-way streams. You get to pay for the gas coming in, you burn it, use it once, then half of it, well, not necessarily half, 20% of it goes out the chimney, and you use it once, and then it all leaks out through the windows and around the doors, and you've got nothing left. So we're trying to figure out ways that we can recapture and recycle heat flows and do the same thing with water. And then we supply the remaining demand with for all of the systems that we need in the building with the most efficient electrical and mechanical systems that we can find. And then finally, to John's points here, we look at maximizing the percentage of the energy resource from renewable sources. And we've also gotten to the point now where the buildings that we do have become so efficient that we don't use gas at all anymore. All of our buildings are all electric, and we're getting them to the point where they're also able to be all electric, supplied by the energy that we can generate on site. Now, of course, that won't be the case with every single type of building, but the things that we're doing, we've really gotten to that point. And so these strategies have been very helpful to us as we've moved through a series of different projects. And this is sort of a complicated slide. We don't have to spend too much time on it, except just the thing that we've really learned that's important is that decisions have to be integrated. We don't just talk about making component parts effective. We want to optimize the whole system, not just the parts. And this turns out to be also something that's not really the norm in the architecture profession. A lot of people still, the architects do the design and they hand it off to the mechanical engineers to design their system and the structural engineers to design their systems, and they don't really talk to each other that much. We don't do it that way at all anymore. Our projects are all very collaborative. The entire team is involved, and it's amazing what we can learn from each other when we talk about the building design together. And also for us, part of our process is that we set very high goals for our projects, and then we just work with everybody until we get there. So this is an example. This is our first LEED Platinum project. It was also the first LEED Platinum building in 5 states. And at the time, in 2006, it was the 4th highest point scoring building in the world. And we, didn't set out to do all of that because we didn't have any idea really what we were doing when we started. But if you can see in the upper left-hand corner, that's what we started with. A 1940s, this thing is less than plain vanilla. It was just a box. Wasn't even a very well-built box, because it was built during the war when there were shortages of materials. When we opened ceilings up, we found rafters that weren't even full length. They were scabbed together. So we can take something like that, that's not a great building, that's not even well built, and we can turn it into a state-of-the-art, high-performance building, and we can do it for less than building new. So this building, lots of lessons learned. Obviously, it's got a photovoltaic array. We have light shelves. We did radiant floor heating. We actually started with some composting toilets. They didn't work in this building for reasons that we didn't understand at the time, but you really need to have your composter closer to the toilets. But the other systems have all worked very well. And the other thing is that we figured out how to do this in this place, in this climate, by ourselves. We didn't have a huge budget. We didn't have a lot of consultants. We just worked with our team here, and we had a client that was interested. We set high goals, and we met them. So this is just a quick analysis that we did of the upfront construction costs. On the left is a conventional approach. If we had built it new versus the green building approach, which is what we did, taking advantage then of the existing building. And the construction is less, the renewable systems were more, but at the end of the day, it was $330,000 less, first cost less, to take that old piece of junk and turn it into a state-of-the-art, high-performance building, and it's continued to perform well. They've actually added a solar canopy in their parking lot, and the building is now net zero. And all the systems have performed well. The building's very durable, and it's been a great place for that client. So another thing that we've really learned, the terms green building versus sustainable building, we hear those terms all the time. But the way that we think about sustainability versus green is that green building is really, how can we make conventional better than what's typical? And sustainable means sustainable, where buildings take care of itself. And so the Living Building Challenge is a program that we found out about, and that I'm going to talk about here in just a minute. But it's really promoting, it's taking lead from moving the market, improving the market, to really trying to get what is the end game. And the end game is to have buildings take care of themselves and be zero in terms of consumption, and in some cases be actually regenerative. I don't know why I move that every time. So this is a little diagram that a friend of mine in Boston came up with that just kind of walks us through what's happened in the last several centuries in the Western world. Housing prior to the 1800s, really prior to about 1900, was pretty simple, but it was not efficient at all, and it was consequently relatively not expensive. It was very difficult to keep these kinds of buildings comfortable. Then we got into the 20th century, and we started adding all these systems, and so they became, houses and buildings became very much more complicated, but they still weren't very efficient, and they were definitely a lot more expensive and a lot more maintenance and more challenges to keep going. And the way that we're trying to move now is to be smart, and that means efficient and inexpensive. So we're really trying to design buildings that can take advantage of the climate and the geography and the characteristics of the place where they're located, the client and their program, and make the buildings work with them, with those factors instead of against them. Which leads us to principle 5, which is create meaningful places. And we found that if we don't do things that people care about, that really work, then we're not really doing anything, because they'll just be, again, a throwaway building. We don't like to think of buildings as novelties. We don't like to think of them as commodities. Another thing that's really happened after World War II is the whole treatment of buildings as a commodity, so that when you're done paying it off in 20 years, it's fully amortized and depreciated, and you can just throw it away. We see that happening all the time, and we're learning that these buildings prior to the 1930s were built to last, and they can last. And there's so much resource that goes into building a building, so much embodied carbon in those existing buildings, that we should not be throwing those things away. We should be figuring out how to take advantage of what they have to offer and using that. Okay, so now I'm going to talk about our house, which is called the Urban Frontier House, and it's located in Billings, Montana. So a few factoids about Billings. 111,000, we're 3,100 feet above sea level. You can see our snowfall there. The 106 inches of max was 2 years ago, and that was a lot. But our average rainfall is about 13.7 inches. The minimum of 7 inches was just about 10 years ago. Our average temperatures are probably a little different than Bozeman. For those of you up in Bozeman, 17 for a low in January, 87 for a high in July. But our records go from minus 37 to 108. So we've got a pretty extreme climate with a relatively low amount of moisture. And we decided that we would build a house that we wanted to build a house that could do all of these things. These were the goals when we set out. And this really goes all the way back to those experiences in college in California, and a desire to see if there isn't a different way to do things. And the time finally came around when maybe we could pull this off. So we wanted a small urban site because there's not enough planet left for everybody to have their 10 acres. So we picked a lot in an older neighborhood right in the heart of town. The low budget, I will have to say, that we didn't quite meet that, but when you're pushing every known envelope, it's hard to do it on the first time. But we are continuing to implement some of these systems in other projects, and we're very shortly going to be able to build houses that are this sustainable for the same cost as conventional construction. We don't want any off-site utilities, and at this point, we only have a grid tie with Northwestern, and we are net zero, but we haven't yet completely been able to deal with the dip in solar production in the wintertime. I'll get to a little bit more of that later. The building needs to be comfortable by today's standards because I have a wife, and if she doesn't like it, I'm going to have a problem. So we've got to figure out how to make that work. It needs to be low maintenance and durable. That's for me because I get sick of painting on the outside all the time. Easy operation. That means that the house can't be operated without special training, then that's not going to really work. And we wanted to do things that were replicable and scalable. So those are our goals when we started this process. But to make it a little bit more challenging, we also decided to go after the most rigorous green building programs on the planet. So we started with LEED. Of course, our goal was platinum, and we have achieved platinum. We almost got every single point available. So LEED turned out to be really easy. The Passive House is an energy program focused, and we have not yet completed documentation, but we expect to make Passive House certification as well. But the really challenging one is the Living Building Challenge that I mentioned earlier. Similar to LEED, it's a holistic look at buildings. Unlike LEED, it's not points-based. Also like LEED, it does take a look at a variety of different aspects of buildings, from materials and energy to water, place, beauty, equity, health, and happiness. So again, part of the idea here is that if you're building buildings that are just machines and they're incredibly efficient, but they're not lovable, they're not likable, they're not enjoyable, then you're really not going to have something that's going to last. So the beauty and equity parts become really important. Again, unlike LEED, this program has the 7 petals, and then among the 7 petals, there are 20 imperatives, and an imperative means simply that you have to do it. So we have submitted all of our documentation for this project. It's being reviewed right now, and we're going to find out pretty soon, but we're optimistic that we're going to become the first Living Building Challenge house certified in the state of Montana, and actually I think only the 3rd or 4th one in the country, because this is incredibly difficult. And we're also doing it in a very much more challenging climate than any of the others so far. So this is our site. Right in the center of that square, if you can see it, is a red dot. It's a corner lot that our house is located on. Just up the block is North Park, about 18 acres of green space. All those yellow dots are different amenities. They're all within that red square, which is about a 10-minute walk. So at the bottom line there is in downtown. So we're just a few blocks from downtown and all kinds of amenities. We're also very close to the ballpark, which is cool because we can walk to the games very easily. Anyway, so again, that's our urban site. It's an older neighborhood, one of the earliest neighborhoods in town. It's a small lot, and as you can see here, it was a view lot. The view is of asphalt. So this had been a parking lot. It actually was originally a house site, and then the state of Montana bought this corner in 1960-something, put a parking lot on it for a state office building, which is kitty corner across the street. Then they were able to secure a site closer about 10 years ago and put this lot up for sale. And so we thought, man, who wouldn't want an asphalt lot? So we took it. It does have a few trees that we've been able to save, that huge Siberian elm, It has been trimmed up, but we kept it, and they're right on the property line. They're all volunteers. So we didn't have really a lot to work with here, but we took what we had. Okay, so then when we got into the design, we really focused on, again, taking a look at optimizing things and strategizing this from the beginning. First of all, orientation. And if you remember that slide I just showed of the site, the streets were all at an angle, and that's because north was up, and our street grid in this part of town is oriented approximately 35 degrees east of south. So we had to deal with the fact that we didn't have an ideal orientation for solar purposes. But again, that was the circumstance we had, so we worked with it. The building shell has been optimized for our climate. Heating and cooling were interesting because at the end of the day, we have no cooling system. We don't have systems for either one. We were able to make this house work with all natural cooling incredibly effectively, and with only a little bit of electric backup heat, no system, we have no thermostats. Water, the water is all collected on the roof, on site. We don't have any city water, we don't have sewer, we don't have a well, we don't have septic. We're completely on our own. We collect the rain and use it several times. And then energy. So the thing you see in this diagram, we've got the solar panels. We also have a 1 kW wind turbine, which was supposed to make up the difference in the wintertime, or the lull in the wintertime of the solar energy. And unfortunately, if you don't have wind, a wind turbine doesn't do you a lot of good. And we had a lot of wind data from with as close as 3 blocks away. And it turns out that wasn't close enough, and it didn't really work out as we'd hoped. So again, just some of the strategies of super insulation, something we discovered called phase change material, which is it's a biological phase change material that we built into the walls. It's worked really well on the cooling side. Now that we really understand how it works, and without having a mechanical system, we should have bracketed our comfort zone and had a cool temperature bio-PCM as well, but we didn't figure that out till later. We do have a heat recovery ventilation system, so we do circulate the air in the house. The temperatures in the house are very consistent seasonally. They do move with seasons, but they're very consistent throughout the house year-round. And then we have a net metered 6.02 kilowatt array. And our energy use intensity without the PVs is 5.1 kilobTUs per square foot per year, and with the solar array, we're 0. So it's not a very big system. It's about a 2,400 square foot house, plus a garden room, plus a garage, and it works really well. So just some insulation to show you what we're up to, because this is pretty interesting. This really happened as a result of the passive house modeling, very intensive energy modeling that we did for this house. The roof is an R85. The walls are R51. The walls below grade are 59. And we've got R76 below the slab. And of course, growing up, I'd always thought it was a little silly you really didn't need to insulate below the slab because it's just earth temperature. And that's true, but the problem is if the earth temperature is any cooler than you want it inside, then you need to insulate it, or otherwise you just have that drip of pulling energy out of the house and dissipating it. So the passive house modeling was very interesting and led us to the insulation levels that we've optimized for this particular house. Come on. Okay, so this just shows the under slab insulation. This is something we worked out with Big Sky Insulations out of Belgrade. It's a custom system that integrates the footings with the slab all in one pour. And it worked out really nicely. And then on the right is the bio-PCM. The phase change material comes in sheets just installed between the studs in the wall. The material that we put in melts at 73 degrees. It says 72, but which again works really well in the summertime because it's very easy to cycle the temperature through that 72 degrees. So we freeze it and thaw it on a daily basis, and it keeps the temperatures in the house very constant. In the wintertime, though, without a mechanical system, we're below 72, so it basically just freezes during the winter, and that's where we should have, and we will in the future, do the phase change material that has both a summertime temperature and a wintertime temperature. So this is our basement, which has all kinds of really bulky stuff in it. On the left, the tall dark blue tank is the composter. All 3 toilets in the house dump into that composter. We've now been living there for almost 4 years, and we have yet to take anything out of it. So all of the toilet waste goes in there, plus all of the kitchen scraps on a weekly basis, and it continues to, biology keeps doing its thing, and we don't have, still haven't had to take anything out yet. The green tank directly ahead is the gray water, biological gray water unit. So all of the drain water goes into that tank and is treated first there and then moved to a storage tank. In the foreground, you see some of the filters and the pumps. We have 2 systems that are parallel, one for gray water and one for the rainwater. The rainwater tanks are right on the immediate right. We've got 6 1,500-gallon rainwaters, and I'll go back and forth here. So they look like this. And then we've got one of the same size that's gray water. All the tanks are connected at the bottom across the floor, and you can see in the foreground there the pumps. So the water is pulled out of the tanks, pumped through the filters into the pressure tanks. Oops, I get to use the other button this time. So I'll go back to the small blue pressure tanks, one for treated rainwater, one for treated gray water. And so the treated rainwater is used for all the potable uses, the sinks and the showers, and that drain water comes back into the green tank. The gray water, after it's treated, is used for the dishwasher, the washing machine, a tiny bit for toilet flushing, and then ultimately irrigation. So every water molecule is used at least twice, many times more than that. But it's all treated the same way. So we've got really effectively potable water all the way. And the water thing has been amazing. And the tanks, going back to this big, you can see some markings on that tank, but where the top starts and starts to curve, and then there's a line, a recessed line in the tank just below the top. That's as low as we've ever been. And so what we've discovered over time, again, almost 4 years now in this house, that we use an average of between 8 and 10 gallons of water per person per day. In the city of Billings, the per capita consumption is 140 gallons in the wintertime and 210 gallons in the summertime. So we're just dramatically less than that. And we're able to do that without, frankly, any sacrifice of water comfort, if you will. We have water anytime we need it for anything that we need it. But the difference is that we have, first of all, very low flow fixtures on the faucets and the shower heads. Also, toilet flushing uses gray water, so we don't even count it. But we also use all the rainwater more than once. And it's been a very effective way to do it. We've been down as low as that first line, which happened the first winter, because I didn't know how to properly weatherize my rain barrels outside. And so we went for 3.5 months without collecting anything. But for the most part, we've been around from about 8,000 to 9,000 gallons. So we have, way more storage than we needed at the end of the day. Okay. So this is upstairs. you can see that there are lots of different colored materials in here. We took advantage of a lot of reclaimed material. That was driven in part by the Living Building Challenge, which required that we either use FSC, Forest Stewardship Council certified lumber, or reclaimed lumber. And FSC is not available in Montana easily. We had one shipment. When that ran out, then we started scavenging. But at the end of the day, we were able to find so much really great stuff that we're now on this case all the time. Those beams, the big glulam beam there, those came out of a school in Lame Deer. They were sitting in a pile. They're all muddy, but we bought them all, and it turns out they were just the right sizes, cross-sectional areas, and lengths to do all the beams that we needed in the house. So all kinds of serendipitous things like that that we found that really made it interesting, because pretty much every square foot of this house has a story. Every board has a story, and it makes the house much richer. There are still people actually that when they come in, they say, this house smells like wood. It's always smelled like wood. I can't really smell that anymore, but it certainly feels like wood. It's got great texture and color. So this is what the house looks like on the outside. That's the wind turbine. But it works fine, but it doesn't generate much energy because we just don't have very much wind. So you can see the asphalt that you're seeing in the boulevards is now gone. That's will be landscaped this spring, but the rest of the house, we have no grass. It's all gardens and fruit trees and that kind of thing. It's all productive, which is also all irrigated by the gray water in the house. So all the water, including irrigation, fits into that 8 to 10 gallons per person per day. This is our interior garden room. What's not quite finished in this photo, but the plants love it in here, and so we're able to grow winter vegetables, but we also have a lot of other plants that help to keep the air clean. And it smells great. The wall of many colors, those are a bunch of boards that came out of a building shelving from the 50s, very dry, very straight, very flat, but not tongue and groove. So we figured out a different way to use it, made something interesting. Again, as an architect, it was all about, at the end of the day, serendipity, which is not what architects like to do. We try to figure everything out in advance. Couldn't do that here. We found, as we found things, we figured out how to use them. The form of the building didn't change, but the interior surfaces definitely did. There's a green post over there in the corner. That actually was an outfield fence post from the old Cobb Field ballpark in Billings. So we found some of those, and again, everything has a story. So this, I'm not sure why this is here, so I'm going to skip right past this, because that's obviously right after it was finished, and it was very bright at that time. Some of the gardens, again, in the back, these really are new. They just went in last year or so, but just a tremendous outpouring of foodstuffs. That was very exciting to see. It turns out if you've got a good setup, plants will grow, and they love the water. So we make all this happen by having a great team pictured here. Everybody's on board with what we're doing. There's constant conversation about how can we improve things, how can we do better, what can we learn, and we've also been working hard on becoming a better business too, so that we can continue to do this and benefit everybody. And this is the fun at the old house, and with our really great team. And I think that's, nope, maybe I got one more. Nope, that's it. So I don't know if there were any questions or if we have any time left. We have a few minutes. I would be certainly happy to answer any if anybody had any.
We do have a few questions that have come up, Randy, and I'll encourage our participants this evening to type your questions into the chat box. I'll just read these as they've come up. The first one, Randy, is how can you have no sewer or leach fields? Pam has asked, how can you have no sewer or leach field?
Well, that is a good question. And as the writer undoubtedly knows, state law requires that if you're building in it within a municipality that has sewer and water services, you're required to connect to it. So I spent an hour with our public works director and got an exception. He took it to DEQ and came back, and we have an exception to do what we're doing, which turns out is really fabulous. And it also turns out that really this is not possible almost anywhere else in the country. But because of the fact that we didn't have to connect, we were able to take that money and put it into the systems that we've developed, which we continue to learn from. We're monitoring constantly. And it really gave us the opportunity to figure out how to make this work. And the answer in terms of how does it work is that it works great. And so we can make a water system in Montana, in the parts of Montana that are pretty dry, work really well if we're given the opportunity to try it.
Great. Randy, if more questions are stacking up here. The next one, how do I explore the possibility of retrofitting these ideas to my current home?
Well, we are looking at, and obviously this was a new house, and so in spite of all the stuff I was talking about with the old buildings, we didn't start there, only because we had so many things we were trying to learn. It just made more sense to not have to deal with any existing conditions. But now that we can go backwards, and so we have worked on a number of properties and buildings where we've inserted these kinds of things. We're doing a project in Lavina right now that will have a rainwater system. We're working on another one in Roundup that will have a water system. We're doing the PVs everywhere. We're doing the optimizing insulation everywhere. Now, obviously, if you've got an existing building, you can't change the orientation. But the key is, again, to listen to the building and see what kinds of opportunities it has. And then you look for how to insert any or all of these kinds of strategies. So it really just depends on what the existing building looks like, how it's put together, as to what kinds of opportunities you might have.
Great, Randy. The next question, explain the biophase change material.
Okay, so the phase change material it's a biological material, so it's made out of natural oils, and the chemistry is set such that they can be designed to melt at whatever temperature you pick. And in our case, it was 72 degrees. And so it acts like an ice cube. There's a lot more energy that's stored in the process of changing the phase from solid to water or from water to solid than there is to change the temperature once it's in a phase. So if you take a glass of iced tea outside in the summertime and it's warm, and as long as you still have ice in your cup, the temperature in the cup will be 32 degrees because that's the temperature that water melts. As soon as the water's melted, though, or the ice is melted, then that temperature will start climbing pretty quickly. And it works the same way going in the other direction. There's a lot more energy involved with freezing it than there is with dropping the temperature further after it's frozen. So we take advantage of that latent heat, which is the phase change, the heat of phase change, and so that when we're cycling the temperature through the 72 degrees, in other words, it's warmer than 72 in the daytime, and that material starts to melt, and it's below 72 at night, and so it freezes back up, and so it doesn't get to that low temperature because it's starting to freeze, and it doesn't get to the upper temperature because it has to melt everything before it can go there. So it creates a lag in the daily temperature swing, and we were able last summer to keep the temperatures over the course of the entire summer between 70 and 76, and on a daily basis with about a 3-degree temperature change, but it would change a little bit over the course of the summer depending on how hot it was outside. So on the hottest times of the summer, we were operating between about 73 and 76, and if it's a little cooler earlier in the summertime, then it was between 70 and 73, and other times it'd be somewhere in the middle. So it works really well. We just wish we'd understood how it really worked, and we could have used it on the cooling side or on the cool side as well.
Great. Next question, Randy. Can this be done on a tiny home as an accessory dwelling unit, or is there not enough room for all that storage under it?
Well, the thing about a tiny home is that there aren't a lot of people in it. And so everything gets miniaturized, and absolutely, tiny homes are super easy because you have very little volume. You have to heat and cool, so it's very easy to optimize the insulation. This amount of storage that you'll need to do this. This is one thing that's probably going to be a little bit more. You might have to have a small shed attached, but you're not going to need 9,000 gallons of water. We don't even need 9,000 gallons of water. So yes, absolutely. These systems can be incorporated into a tiny house, and we think that's really a great opportunity to use these kinds of things.
Great. Next question. MSU is drilling thermal wells around our building to replace using standard steam system, gas. Are you familiar with this?
Yes, what they're doing is a geothermal heat pump. So they're taking advantage of again, it's kind of like the phase change material. They're taking advantage of the heat of the earth, which, and with a refrigerant running through these lines, you can make it work where you can pull heat out of 50-degree refrigerant, or you can put heat into it. And so the earth then acts as a giant heat sink, basically, and the temperature doesn't change that much. But the fluid that you cycle through it then either discharges heat to the earth or picks up heat from the earth, and it's able to be used with a heat pump. So it's a great system. There's a very high coefficient of performance, meaning you can generate more than 1 unit of energy for every unit of energy you put into the system to operate it. However, it is expensive. And what we've found, so for an existing building on campus, it probably makes a lot of sense. But what we've found for something like our house, because people have asked if we did that, and we say no, and the reason is because for us, that would be a little bit like jumping into the space shuttle to run down to the corner grocery store. It's just too much horsepower. And so it would be very expensive, highly underutilized equipment for something as optimized as our house is. So it kind of depends on where you are. I mean, if you can really get the building to perform well, because what we like are capital costs. The insulation is a capital cost. There's no inputs required once it's in place, and if it's optimized for the climate, it never needs to be changed. It doesn't wear out. It doesn't require any inputs of energy or water. Same thing, that biophase change material will last for, it was tested to be 85 years and still hadn't failed. So we like to do things that are really geared to the place, to the climate, to the orientation, and make those capital costs and let that do as much work as possible. And then if you do need efficient systems, depending on the project and the building, a geothermal heat pump can certainly be a really great system. But sometimes it's just too much.
All right. The next question. Was heat produced in composting process considered for heating the house?
Yes, I can absolutely say that I was counting on it, as a matter of fact. But it turns out that the heat that is generated from the composting is really contained within the composter. It's very well insulated. And so I was expecting that the composter would actually become a radiant source down in the basement. But, it's not cold, but it doesn't, we're not really getting any heat off of it. It really does stay contained. So, and if I tried to circulate something and pull heat out of the inside of the tank, then of course that would disrupt the composting. So it turned out not to be an effective heat source. And since we're still looking at this photograph, you can see the refrigerator in the corner over there. At one time, I was working on a whole strategy where I could exhaust air to the outside in the summertime and then keep the heat in the wintertime. As it's turned out, I didn't get to all of that. It got too complicated, but it also is a very efficient refrigerator, operates less than a kilowatt hour a day. So it just doesn't generate very much heat. And in the wintertime, when the house cools off a few degrees, about 10 degrees, the energy consumption drops about 20%. I mean, we go from 0.96 kilowatt hours a day in the summer to about 0.72 kilowatt hours a day in the wintertime, just from the house being cooler. So for all of you that have your beer refrigerators out in that really hot garage, think about it, because that's a really expensive way to keep beer cold.
Great. This next question has two parts. First, what's the roof made from? And then also, what do you plan to do with the contents of the compost tank? Will it need to undergo further processing before use in, say, a garden?
Okay, two good questions. So the roof is corrugated galvanized metal, 24 gauge, and the siding is just cold rolled steel, 24 gauge, just flat stock that's been fabricated. So both also 24 gauge. So both are very durable materials. The corrugated on the roof, we've been hailed on a few times. You can't even find a dent. I mean, there might be a dent possibly somewhere, and there were windows broken out just a few blocks from here. But the corrugations really conceal any dents. And then the rusted metal on the siding, same thing. I mean, first of all, it is a flat siding on a flat solid substrate. It's a 24 gauge, but there are no dents perceptible because it's also a very matte finish. So it's not painted, it's just rusted. You can't see any dents or anything in it. So again, that was part of the durability factor. It also was pretty inexpensive, and it's recyclable at the end of its useful life in 200 or 300 years. Then the compost, we have a composter outside that it's a 2-cell composter. We do the garden scraps out there, and I'm going to double compost the inside compost with the outside compost when we ever get any, because as it turns out, we're just not going to have much volume. And so I'm going to use that to feed into the outside garden scraps composter. So everything will be double composted before it gets put on any gardens.
Great. Another question, was the team able to track all of the aggregate efficiency or embodied energy that went into this project?
Well, I have to tell you, that was a requirement of Living Building Challenge, and it's an incredibly challenging thing to do. So we've done some of that. I really hope we're going to pass muster. I have to say that was, at the present time, that's a really difficult thing to do. And again, this house was done all internally. We didn't have any consultants. We're not paying people to do this stuff. We're trying to figure out how to fit it in around more bill-paying types of projects. So yes, we did work on those issues. We dealt with the bigger materials. We didn't necessarily get everything fully documented. But we also didn't have, one quick follow-up. We don't have a lot of high embodied energy products. The concrete, which is one of the highest, about half of our concrete is 100% fly ash concrete, and the intention was that it would be all fly ash concrete. So it's very low embodied energy at that point, or carbon. And but we had a failure with the batch plant, and so we had to give that up and went to a percentage of fly ash and some Portland cement. The steel is largely recycled, and then the vast majority of the other materials in here are reclaimed. The kitchen cabinets that you can see in that upper left photo, those are all made from beetle-killed wood harvested in central Montana. So really, mostly, I mean, the vast majority, the vast volume of material in the house is reclaimed or low carbon to begin with. So, sorry.
Great. Another question just came up. To be even more efficient, your house could be smaller and have used less resources. Do you think you could live comfortably with less space, what space could you sacrifice?
Okay, this is a really good question, and my wife's still in the room. So one of the criteria for this house is that we have 7 kids, and she said we have to be able to sleep all 7 kids, plus any spouses and future grandkids in the house at the same time. So the house is a little bit bigger than I would have had it. Although we don't have a ton of bedrooms, we have all kinds of places where people can sleep. We've got little lofts, we've got a secret room. We've found nooks and crannies, and we have slept 16 people in this house. That's our record so far. So it is a little bit bigger. Yes, we could certainly live in a smaller house. It would be easier if it's smaller. The larger it gets, the more challenging it becomes in certain respects. But this was a compromise that we worked out so that we can get all the kids home if they ever choose to come home at the same time, and camp everybody.
Great. And what was your square foot cost?
The square foot cost is around $182. In our market, for comparable quality, I mean, it's not going to certainly be the same, but comparable quality is about $150. Now, this is several years ago, but that's where we are. So we didn't quite meet our goal of being equivalent to market-based stuff, but we're not that far off. And a lot of that additional cost was just a learning curve.
Great.
So we can use that next time.
We have a couple of minutes for any last questions. And Randy, while we're seeing if there's any last questions, any last thoughts? And how could folks get in touch with you if they wanted more information?
Well, they can get in touch with us through our website at highplainsarchitects.com. I should have had that. It's down here in the corner, but we didn't put the...
I'll get that up. I'll get that up for everyone.
Anyway, it's just highplainsarchitects.com. And I guess the thing that the point I really want to make out of all of this is that I think we're in a world of hurt from a climate warming standpoint, but there really is a way to live on this planet a lot less destructively. And this is only Gen 1. We can go a long way from here, but we learned so much. And we were very interested in doing this in a rigorous climate, which we are. And it's really been very successful. It will only get better as we learn more and continue on. And so, yes, and obviously we're going to need to figure out how to do this with existing buildings, and we can. The lessons that we've learned here are replicable, they're transferable, and we can, and they're scalable. You can go both ways, up and down. We're working on a 51-unit apartment building that would look to do all of these kinds of things and be completely self-contained and self-sustaining. That would be a new building, but we're employing these same kinds of measures in existing buildings more and more as we're developing new projects. So we think that's just a tremendous opportunity, and not only is it an opportunity, though, it's a necessity. And I just can't encourage people enough to really get outside the box and think about different things. And if you don't have another question, I'll tell 2 quick anecdotes.
No more questions. Go for it.
Okay, so one is, because one of the other things we got interested in is solid waste. So how much trash are we throwing away? And in a house like this, you don't really want to be hauling the garbage out every day. So we're at a place now where we take out 2/3 of a cubic foot of trash for the entire house every 3 weeks. And when you get down to that point, you start to figure out what's left. And it's mostly really unfortunate non-recyclable plastics. The clamshells that produce comes in, that kind of thing. And we should just get rid of that stuff. We don't need it. Because otherwise we can. In Billings, we don't have a super sophisticated recycling program, but we can recycle or compost everything else. And then one other thing I just wanted to mention in terms of things that we're trying to do, close loops, make things as efficient as possible. When we set up, we do have a dryer. It's electric. It's very efficient. We also have a clothesline. But the idea was that in the summertime, if we had to use the dryer, I would vent it outside. In the wintertime, we'd vent it down in the basement and reclaim the heat. But what I hadn't really thought about until we got there is that we have a heat pump water heater in the basement. So we just vent into the basement all the time. And that way, all the water that gets used in the laundry cycle, if it doesn't come back down the drain from the washing machine, if it's evaporated out of the dryer, it gets dumped into the basement. Then the heat pump water heater turns on and extracts the heat from the air. So we reuse the heat energy, and we also dehumidify the air so we collect all the water. It's worked incredibly well. It's really simple. We just had to co-locate these things. So there's lots of ways to think about reclaiming, recycling, reusing, repurposing, closing loops. And if you start thinking in those terms, it gets to be pretty interesting how all of a sudden everything doesn't just have to be a one-way in, out, pay for it, pay to buy it, pay to dispose of it kind of system. We can change.
Wonderful. Randy, I don't see any additional questions. So with that, maybe this is a good time to wrap things up. Lots of accolades coming in, you can see in the chat box. And I'll just say a big thank you to you, Randy. We're lucky to have you in the state and as a resource. So thanks so much. And I just glanced at your website and some great resources there as well. Also, big thanks to Ann Reddy for organizing this and other Earth Day events. And thanks so much. We're lucky to have you as well. So with that, if there are no further questions or comments, we will say until the next webinar, thanks everybody. Be well, stay safe, and stay positive. Take care, everybody. Good night.
Thank you. Good night.